All right, let's open up our kinematics unit with talking about a few motion basics. We'll start with some simple definitions. Every quantity we measure in this class we'll classify as either a scalar quantity or a vector quantity. A scalar quantity is a measurement that has a magnitude only, right? Whereas a vector quantity is a measurement that has both a magnitude and a direction. So let's see some examples of this. So for each of these, are they a scalar or a vector quantity? The first is 5 meters. That doesn't tell me any direction that 5 meters is going or headed, so I'm going to refer to that as a scalar quantity. Whereas in this next example, 30 meters per second east, that does give me a direction. So I'm going to classify that as a vector quantity. 20 degrees Celsius, no direction there. That's going to be a scalar quantity. 4,000 calories, again, no direction, so that's going to be a scalar quantity. Negative 10 centimeters. Now, you might think that's a scalar quantity because it's not east, west, north, south, forward, backward. But in physics, this negative sign does give me a direction. So that's going to be a vector quantity. Another important distinction to make is the difference between distance and displacement. Distance measures the length between objects or points without regard for direction, right? So in this example here, right, the total distance that this object is taking, we have to look at the entire path that the object is going, right? So we're looking from point A all the way through to point B. This is going to be a scalar quantity, again, because we don't really care about which direction it's going, but it is path dependent. Okay. Whereas displacement, as you can see in this diagram, it's an object's overall change in position. Right? It is a vector quantity, which means direction is important, but it does not depend on the path taken. Right? So we can see the difference between distance and displacement is displacement, we just care about where it starts in relation to where it ends. We don't care about anything going on in here, right? Just start to finish. So let's look at an example of this. Jim travels 60 meters west to go to Cindy's orange house. Okay, so Jim's traveling 60 meters west. However, Cindy's not home, so he decides to head 40 meters east to hang out with Harry at his blue house. Right? So what distance did Jim travel? Remember, distance, it depends on the entire path taken. So he traveled 60 meters first, then he traveled another 40 meters for a total distance traveled of 100 meters. For displacement, remember, direction is important, so we have to assign one direction to be positive. It's usually a good rule of thumb, whichever direction or whichever motion is mentioned first, let's make that positive. So let's make the left positive, right? Which means he traveled 60 meters in the positive direction and then 40 meters backwards or in the negative direction, giving him an overall displacement of 20 meters in the positive direction. Another important distinction to make is the difference between speed and velocity. So speed is taking the object's distance traveled divided by the time interval. It is a scalar quantity, so we don't need to include direction here. Whereas a velocity vector is taking the object's displacement divided by the entire time interval. And it is a vector quantity, so that means we must include a direction whenever we talk about velocity. Now looking at instantaneous versus average velocity. Instantaneous is a velocity at a given point in time. Right? So a great example of that is your speedometer. If you're driving down the highway 60 miles an hour, right, that's how fast you're going at that moment. Whereas average velocity looks at the overall change in the object's velocity over the entire time period. So we do have a new equation for this, and that's going to be x is equal to x sub 0, otherwise known as x naught, plus velocity times time. So that's going to be our first big equation. We can rewrite that if we want, depending on what we're looking at. So I could subtract the initial position over here. So that would become x minus initial position is equal to velocity times time. And final minus initial we can refer to as delta x, or change in x, which is equal to velocity times time. So that's kind of two different ways of writing the same constant velocity equation. So let's do another example. Jim and Harry are walking to the bus stop, which is 0.5 miles to the left of Jim's house. It takes them 20 minutes to arrive. As soon as they get to the bus stop, Jim realizes he forgot his lunch and runs back home, taking 10 minutes. He then rushes back, which takes him another 12 minutes. So what is the average velocity in meters per second for the entire trip? Well, the first thing that I notice is I'm given all my measurements in miles and minutes, but I don't want miles and minutes. I want meters and seconds. So let's get those units converted. First off, 0.5 miles. I know that there are 1,609 meters in every 1 mile. I've put miles on the bottom so I can cancel out miles on the top. And if I do 0.5 times 1,609, I get 804.5 meters. Okay, so that'll be helpful. Now looking at time, it's asking me for average velocity, so I'm going to need the total time interval, or the total time it took. So looks like it takes them 20 minutes to get there. He runs back home, so adding another 10 minutes to the trip, and then rushes back in another 12 minutes. So all in all, that is a 42-minute journey. So let's get 42 minutes into seconds, because that's the unit I'm going to need my velocity. So 42 minutes, and I know that there are 60 seconds in 1 minute. So minutes will cancel, and I will get a final time in seconds of 2,520 seconds. So those values are going to be helpful when I start doing my calculations. Average velocity is displacement over time, right? And if Jim goes forward 804.5 meters, then backwards 804.5 meters, and then forwards again, his overall displacement ends up just being 804.5 meters in that 2,520 second journey. So he has an overall velocity of 0.32 meters per second. Now, for looking at average speed, remember, speed is the total distance traveled divided by the time interval, right? So I have to look at the entire path he took. and that was the first half mile plus the next half mile as he walked or as he ran home, plus another half mile when he was heading back to the bus stop. And he did all that running in 2,520 seconds. So he has a total speed then of 0.95 meters per second. So if he's not moving in a straight line, that velocity and speed value are going to be different. Let's do one more example. So Cindy is running a 5K, 5,000 meter loop for her first cross-country meet. Jim wants to make sure he's at the finish line when she finishes, but he also wants to get a hot dog. Cindy usually runs with a speed of 4.3 meters per second. So how long does Jim have to get his hot dog? Well, if I'm looking for time, right, I have a couple variables to play with. I know speed is distance over time. We know that she runs with a speed of 4.3 meters per second. She's running a total distance of 5,000 meters. So how long is that going to take? I can do some rearranging here to find a total time of 1,163 seconds. That's how long he has before she finishes the race. Next question is, what is Cindy's average velocity when she finishes the race? Well, remember, velocity is displacement over time. Now, if she's running on a track, she's maybe starting here and doing a couple full loops and ending right back where she started. So if that's the case, what is her overall displacement? You're right, her displacement is 0. So because her displacement is 0, therefore her velocity is 0. If she's not running in a straight line, velocity and speed measurements are going to be very different. So why does her velocity differ from her speed? She travels 5,000 meters, but because she ended up back where she started, her displacement was 0. All right, and that's it for the motion basics. Jot down any questions you might have, and we'll chat about them in class.